Hi. You know what? This is the last chapter in the book we're covering today. So this is chapter 20, Integral Equations in Quantum Mechanics, in 2 units. Okay. Congratulations if you've made it this far. Okay, so today we're going to talk about integral equations in quantum mechanics. So it's both a lecture on integral equations, and that maybe is the most important part for many of you, the fact that you can solve integral equations much the way you solve differential equations or partial differential equations numerically on the computer, quite straightforward. But also that you can view quantum mechanics in an integral formulation. So there's 2 parts, parts 1 and 2. Part 1, which is what we'll talk about today, talks about bound states. Okay, that's the easier part. Part 2 talks about scattering, and we call that optional. It involves some other new numerical aspects dealing with singular functions on the computer. So that's more advanced. I would actually call it graduate level. But the undergraduate level part would be bound states. You study that with differential equations. Now we'll study it with integral equations. So let's get going. Here's your problem. You need to solve a bound state problem in quantum mechanics in momentum space. Why do you even have to do that? Well, the reason you have to do that is in many applications, in fact, most if they're done carefully, if you have a many-body system, such as these blue spheres representing atoms or molecules or nucleons or quarks, for that matter, interacting, say, with a projectile. So the projectile's here in red. It's passing amongst these other many bodies. And if you try to describe this by a simple Schroedinger equation for just one particle here, the red particle, interacting with some potential, the potential you get is not the ordinary kind of potential. It's not a fundamental potential. It's an effective potential. And it turns out to be a non-local potential. Okay? And so that's why we have to go to momentum space. So let's see. If you look more carefully here, look at equation 1. And what you see in equation 1 says that it looks like the Schrödinger equation. This is just h times psi, right? Here's the kinetic energy term, right? And here is the potential energy term. Fine. But the difference here is that the potential energy at point R that this projectile, interacting probe, whatever, feels depends not just on the wave function at that point, but on the wave function at all other points in space as well, because there's really particles interacting at all these other points. Think of it that way. That there's not just one particle interacting in one place, they're all over space. So to calculate what's going on at point R, which is what we have in the equation here, R, we have to integrate over R prime over all of space. And the potential we get, this V of R and R prime, is known as a non-local potential. Non-local because it doesn't occur just at R, but it occurs over all of space. And so we have to integrate over the non-local potential and the wave function. So we get equation 1 is actually the Schrödinger equation with a non-local potential. And if you look at it, you realize, wow, it's a heck of an equation. It has sort of everything going for it, other than time dependence, which we can do as well. Okay, what does it have going for it? Well, it has a differential part here, second order differential in the wave function. So it's a differential equation. But then it has an integral. So it's an integral equation as well. And why is it an equation? Why is it not just evaluating a function by integration? Well, the answer is because we're integrating over psi of R prime, but psi functional as a function of R or R prime is what we don't know. It's what we're trying to solve for. So the unknown quantity psi appears both on the right-hand side here, appears on the left-hand side as a differential, and it also appears under the integral sign. So we have to integrate over all space, and we have to integrate something we don't know over all space. We have to solve that. That's an equation to solve, okay? So your problem, your work problem today, is to try to solve for bound states. Try to make the simplest possible bound states as L equals 0, zero angular momentum bound states, calculate the wave function, and calculate the energies for the bound states of this quantum system. The quantum system being a many-body system approximated by an effective non-local potential. So let's go on and say, how do we do this? So look at this next slide. This next slide talks about the theory we'll use. And the theory is the Schrödinger equation, as always in quantum mechanics, in this case done in momentum space. And one of the aspects of quantum mechanics is that it can be viewed either in coordinate space, r space, or it can be viewed in momentum space. They're both equally valid, and they're both equivalent to each other. One can actually transform from one to the other. In fact, when quantum mechanics first got started, both spaces were used, and many of the terminologies you hear about in quantum mechanics, like matrix elements, potential matrix, T matrix, S matrix, are matrices because quantum mechanics is viewed as a matrix problem also. Contemporary textbooks tend to view quantum mechanics just as in terms of differential equations, but it doesn't have to be that way. Okay? It's just our limitation, or that's just the path taken. So for many problems in physics, more complicated problems, more realistic problems, problems dealing with many particles, for those type of problems, dealing in momentum space is often the way to go. So what we have now, if we take that integral differential equation, try to say that fast, okay, integral differential equation, and convert it to momentum space, we get a very simple equation, here equation 1, in momentum space as the Schrödinger equation. So let's look at equation 1. It's just our old friend before, the Schrödinger equation. This is just H on the right-hand side. This is the kinetic energy term, which is just k squared over 2m, k being the same as p, being just momentum. Okay, and these are units in which h bar is 1, so wave vector momentum is the same. So that's k, and this is v, the potential. So in momentum space, we have an integration over the wave function in momentum space. On the right-hand side, we just have the same energy, the eigenenergy we're looking for, and the momentum space wave function. So in momentum space, we no longer have an integral differential equation. We have simply an integral equation. It's still a heck of an equation to solve because the unknown psi of p is also under the integration sign, as well as being other places, but the other places are not differential. Okay, so we only have to concentrate on the integration. So, very nice. What is this v of k and p? Well, in a sense, if you know the potential in coordinate space, you know its momentum representation. That's what it is. So specifically, it's given here by equation 2, which is just the double Fourier transform of the potential to momentum space. Now, it's a double transform because we have two variables, r and r prime in coordinate space we need to transform. It's actually a Bessel transform, spherical Bessel, but the first spherical Bessel function is just sine x over x, so we just get two sine transforms. So we get a sine kr to go with the r differentiation, derivative, and then we get an r prime going with sine p r prime. So that gives us v of k and p. Okay? So that's how you can calculate it, or you can be given. That's pretty simple. And now what we have, psi of p, is just the momentum space wave function. It's what a wave function looks like in momentum space. Okay? And it's just, again, the transform. In this case, the wave function only has one variable, so it's a simple, single transform of the wave function psi of r by just J0, spherical Bessel function lowest order, or sine kr over kr, and the over kr cancels off some terms there. So that's the wave function. Okay, so we have our problem here. We want to solve this integral equation as given. Assume you know the potential. We need, if you want to, you can calculate the potential from any given potential, and we want to solve for the wave function as well. And we can invert these equations, go back and forth to coordinate space if needed, but we're just looking for the bound state energies and wave functions, and we can do that in momentum space just as well. So let's get on with it. Next slide, please. Okay, so where are we? We have an integral equation to solve. Well, the way we evaluate integrals, as you recall, is by replacing the integration by a sum over integration points. Okay? So we replace the integral by a sum, and that, when we do that to the integral equation, that will lead us to just a set of simultaneous linear equations to solve. And when you hear someone say, oh, a set of simultaneous linear equations, that should make you feel warm and fuzzy, both because we've studied linear equations and because they're easy to solve. You just use matrix techniques, and someone else has devised libraries of excellent matrix techniques, and we recommend you use those rather than write your own, so you don't have to do the hard part. Okay? So once you can get it down to a matrix problem, you're home free. Okay? And that's all we'll do. So here we have, in pretty beautiful red dots, those are the grid values. Now they can be any integration rule you want. I almost always recommend Gaussian quadrature to start with. So it's industrial strength. It works so well. So these would just be the Gaussian quadrature points. So if you have no idea what I'm talking about, it's probably too late for you if this is really the last chapter in the book. But anyway, you may want to go back, review the chapter on integration. Okay, so we talk about Gaussian quadrature points there. You may want to go back and read the chapter about linear algebra. We talk about the libraries and the type of equations to solve. I'll assume you're all expert on that, and let's move ahead. Okay, so we want to solve that integral equation on a grid corresponding to the Gauss points. That may not be clear to you what that means, but it will be shortly. So we have this integral. This is the integral that occurred in the Schroedinger equation. Integration over potential, wave function, and p squared, whatever. And we have to evaluate that. Well, we replace that integration from 0 to infinity by just a sum of Gauss points, 1 to n. And what? We have each variable is repeated. The dp is not. There's a p squared. That's just a grid point called k here. There's the v. That's just the potential. And then there's the wave function psi of p. That's repeated there. So we're integrating over p here. So that's the second variable. And that's why the second variable of the equation gets repeated. Notice, however, that we still have a k variable here in the potential, which is just general. That's what appears in the Schrödinger equation. Okay? So this is the hard part. We've taken the integration here and replaced it by a sum. Okay? We have an extra term here, w sub j. These are just the integration weights. You know, for Gaussian quadrature, the zeros of the Legendre polynomials, but it doesn't matter. There's something you look up in the table or the computer gives you. So that's all we have to do. So now the integral equation we had on the previous slide, and I'd show it to you here, but I don't have enough room. There's just so much real estate, becomes equation number 2. So equation number 2, aha, it's not an integral equation. These are just sort of algebraic equations. They're not yet linear equations. Why is that? Well, because we have here how many unknowns? We have this unknown function psi of k, and then we have on the right-hand side the value of this function at k sub j at n points. Okay, so it's the sum from 1 to n, so that's n numbers. So we have n unknown functions of functional values and one unknown function. Okay, so we have just too much here to have to solve. N unknown values of the wave function at the grid points. We also don't know what the energy is. Whoop, and you know what I just noticed? There is a psi of k missing right here. Not missing anymore. Remember it because it'll disappear when I hit the button. But there should have been a psi of k there. That's the E psi term. Sorry for not noticing it before. So we have one unknown. The energy here is unknown as well. The function's unknown. And the trick now is to say, let's not solve this for all possible values of k, of which there's an infinite number, uncountable infinite. Let's just solve it for the same values of k at which we did the integration. So when we do that, we'll get n coupled equations, but they'll be simultaneous linear equations, n plus 1 unknowns. n equations, n plus 1 unknowns. Okay, so we still have some figuring out to do. We still have some problems to do, but we're getting there step by step. So let's look at the next slide where we do at least some of these steps, keeping in mind we need another equation from someplace. Keep it in mind. Don't let it block you, but just keep it in mind. Okay, so here's our next slide. Take a look. So here on top is our beautiful grid points. And we're going to solve the integral equation for values just on the grid point. So now if we take that integral equation, which we changed into algebraic equation, and we evaluate it at k values, which before could be anything, we say, let's just evaluate it, the equation, at n possible k values. And the n correspond to the n grid points. We get equation 1 here. Well, equation 1, of course, since I could be anything from 1 to n, is actually n equations. Okay, so this is n simultaneous equations. Those are the equations we have to solve. So for example, if we take n equals 2, which is not very good approximation numerically, but at least gives you a feel, then we'd have 2 simultaneous equations, and they're given here. So you can see, oh, there's now a psi on the right-hand side. It came back. Maybe it's just an illusion that wasn't there. And you see on the right-hand side, there's the unknown energies. There's the wave function psi, evaluated the 2 grid points. And notice on the left, this is also psi at k1, but then in the integration here, there's also psi of k2. So there's simultaneous coupled integral equations. So we have to solve both. That's psi of k2 there. It appears here in the equation with k1, but here k2 has k1 appearing there. So they are intermixed equations. So that's what we have to solve in general for all n. So how do we do that? Well, look at this. Okay. So we have equation 1, n coupled linear equations. Linear because the unknown is psi, the wave function, and it's linear in psi. It's also linear in E, which is an unknown, so it's linear in both. So that's good. How do we solve this? Well, we want to say this is really just a matrix version of the Schrodinger equation. It's just H psi is equal to E psi, where now psi is an n by 1 vector. So we have here the Schrodinger equation. Okay? So if we write out these n equations simultaneously, we get a matrix. And here we have our wave vector, psi of k. And notice, what did I just call it? I called it the wave vector. The term wave vector comes from quantum mechanics viewed in matrix terms because this is now just a vector. It's an n by 1 dimensional matrix, which is a vector. So the wave vector is in fact, wave function is a vector. It occurs on the left-hand side of the equation, and it occurs on the right-hand side. Okay? So that's the same wave vector psi of k, which is psi. This is the eigenvalue E, and the matrix here is the Hamiltonian matrix. Hamiltonian is often called a matrix or operator, and the Hamiltonian H is, of course, just equal to kinetic energy K plus V. And if we look at the matrix, we see, oh, that's the Hamiltonian matrix. This is just K squared over 2 mu being the reduced mass for the problem. That's just the kinetic energy term. And then along the diagonal here, we have the potential we're adding in, and the potential gets added in with the K squared and the weighting, just from the way we formulated the Schrodinger equation. And the off-diagonal terms are just the potential. So the potential fills up this matrix. It's V's every place here, but K plus V along the diagonal. So that's the matrix equation we have to solve. So, oh, goody. Somebody else can now do all the hard work. We can just go ahead and talk about solving this equation. Look at this next slide. What have we forgotten? We have forgotten the mathematics. We have n plus 1 unknowns because we don't know what the energy is, and you really can't solve directly for n plus 1 unknowns given n linear equations and simultaneous linear equations, okay? That's why this is an eigenvalue problem. There's no guarantee that a solution exists, and only sometimes are we lucky if we search can we find energies which also satisfy this equation. So how do we get around that? How do we get another equation? Well, let's look. Let's try to apply some mathematics here and be clever, okay? So in equation 1, we have our Schrodinger equation. H psi is equal to E psi. We can move the right-hand side to the left-hand side. In other words, subtract E times psi from both sides. Subtraction is always a legitimate operation. So if we do that subtraction, we have equation 2 here. If we look at equation 2, we could say, aha, why don't we multiply by H minus E, the energy, times the unit operator, I. Okay, so there's our matrix. Why don't we multiply by the inverse? Okay, so take that. If we multiply it by the inverse of H minus E psi, we're just left with psi. So we have a solution of psi is equal to H minus E I inverse times 0. 0 is just a vector of 0 elements. Well, that's sort of a lousy equation to have to deal with. It tells us something's wrong. If this is a correct operation, if everything we did is legitimate, then the only solution would be the trivial one, the wave function 0. Nothing happens. But psi identically equal to 0 is in fact a solution of the Schrodinger equation. It's not an interesting one, but it's a trivial solution. It's a possible solution. So we must have done something wrong. In order for that to be a non-trivial solution with substance, an interesting physical solution, we have to have done something wrong. What have we done wrong? We've done so many things wrong in my life, it's hard, that's not a good question to ask. What have we done wrong in just these 2 or 3 steps? Well, what we've done wrong is we've assumed that this inverse here exists. Obviously, if the inverse exists, then only the trivial solution exists. Therefore, the inverse must not exist if there is to be a non-trivial solution. I said it right. You can play it again if you want, but I'm not going to say it again. Okay? So, when does the inverse not exist? The inverse does not exist when this determinant of H minus E I is equal to 0. So, in order to have a determinant equal to 0 means that the inverse does not exist, and that's another equation. That's the bound state condition, as it's called. In order for these Schrodinger equations to have a bound state solution, this determinant of this matrix must be 0. So mathematically, we have 2 options. Okay, we can solve this problem as n plus 1 equations. 1 equations being that the determinant is 0, or we can try to solve it just this determinant problem and look for the eigenenergies. Because if you look at equation 4 here, I just looked at it. If you look at equation 4 here, you realize the wave function doesn't appear. So if we can solve equation 4 just for the energies, we can get the eigenenergies without ever solving for the wave functions. The other choice is you can also solve for wave functions and energies simultaneously. So there's a number of mathematical possibilities, but that's a condition. That's one equation, the only unknown being the energy. The Hamiltonian's known. So this is how we can solve for the eigenenergies, and then once we know the energies, go back, substitute the energies, and have n equations and n unknowns. So we're home free, believe me. Okay, so let's go ahead and look at a real problem to solve. Well, we're going to solve now the delta shell potential. So it's sort of a very simple model for potential, but analytic solutions exist both for bound states and scattering, at least solutions that we can check our numerics with, so it's very handy. So this is a potential in which 2 particles interact only when they're a distance b apart. So if I try to draw this here, what we're saying is if we have a potential at the origin here, okay, so imagine the origin being inside the sphere here, okay, then it interacts only in this shell of radius b from the center. So this is a particle inside or outside. Bound states tend to be inside, but predominantly inside. This is a particle which feels nothing until it hits the shell, and when it hits the shell, it feels an infinitely strong potential, but only feels it for one place in space, and therefore it's not really a singular problem, and actually the wave function can leak outside of the shell because it's not truly infinite, or you can scatter and get inside. So it's a shell. It's called a delta shell potential, and it has analytic solutions, and it also has a nice feature that if this is the potential, it's local in coordinate space, doesn't have an r prime. So when we evaluate this integral to find the momentum space representation, we find that it's just sine kb sine k prime b over kk prime. So that's its momentum representation. It looks good, but it says here too slow to decay. So what we have here is we have to evaluate integrals in an integral equation. And this function falls off just like k or k prime, which is slow, because those integrals barely converge, and it oscillates a bit, which helps, but you end up with integrals which are not just barely convergent, very hard to get convergence. So we don't expect the numerics to be very good. Okay? But other potentials with Gaussian fall-off have much better numerics, but they don't have anything analytic to check with, or a simple form for the potential that you could use here. So for pedagogic purposes, we're going to do a problem which is hard to get correct, very accurate numerically, but we'll go ahead and do it anyway because it's easy. Okay? This potential is nice in that it has one bound state only, and it has a bound state at energy E minus kappa squared over 2 mu, so some value of kappa, and that kappa is a solution of equation 4. Okay? So there's a transcendental equation here, the closest you can get to an analytic solution, and it determines the value of kappa, the wave vector, for the bound state. And what you can see here is, oh, well, in order for there to be a solution, there has to be, of equation 4, two conditions must be met. Number one, lambda must be a negative number, because the left-hand side here is going to be negative, because kappa and b are 2 kappa, e to the minus something, is going to be less than 1, and then we'll have a negative number. So lambda has to be less than 0. That's good. That's saying only attractive potentials have bound states. Okay? Lambda less than 0 means it's attractive. So a particle will be bound only if it's attractive. And then lambda has to be large enough so that 2 kappa over lambda is a small number, which is what the left-hand side tends to be. So that's right. You have to have a certain strength, and it has to be attractive. So as an exercise, which you can take a break right now, say, find the values of kappa which solve this equation for b equals to 10. Okay? And try different values of lambda. I'm not going to tell you what lambda is. Try some lambdas. See when you can find solutions. Okay? So good time. You could take a break right there and then come back. I'm going to keep going, but you could take a break. That's okay. So let's look at the next slide. Well, the next slide says all we have to do is now just use some matrix algebra routines. Okay, so we have this code we've given you. It's not very interesting. Actually, what it does is it just sweeps through all the parameters and lets you pick out what we want. But if we look at the code here in HTML format in detail, so let's see. I know it's hard to see, and I won't go through the whole code, but here's the relevant part. And what you see here is we have A is our Hamiltonian matrix. Okay? And you can see here, so most of the work is here setting up. This is just, you'll recognize the potential elements. This is just, what we're adding on, and now we have the potential elements, and now we're adding on the kinetic energy term, and that's it. Once we have the vector, the matrix A, in Python, which is what this code is in, we can just call eigenvectors. And the eigenvectors will give us both the eigenvalues and the eigenvectors numerically for this matrix. So it solves the eigenvalue problem, and that's what we have. And then to get the real eigenvalue, we just look at the real part of EV, one of the variables returned, And the imaginary part, which may or may not exist, would be the imaginary part of that. So we can get the energies, we can get the eigenvectors pretty easily here, and we can get back. Okay, so what do you have to do? What you have to do is either write your own code or use ours. Feel free to use ours as a model. I recommend you use Gaussian quadrature to have enough precision. And then two possible library calls. The one you've just seen now is we just solve the eigenvalue problem completely, which is to find the eigenvalues and the eigenvectors simultaneously. That's one approach. It may not be the most precise, but it's one possible approach. The other approach, which I've used in my research, is to more often, for more complicated problems, is to actually just solve for the determinant and use a search code, some bisection algorithm or something fancy, a Newton-Raphson, to determine when the determinant has zeros. So this might be more accurate if you just want to get the eigenvalues, or quicker, and it gives you all the eigenvalues for which there's a zero. Now, you can use the problem solver. Both of these are still search routines. There's no guarantee of there being a solution, and they work iteratively. So sometimes they can be fast, sometimes they can be slow, sometimes they can be failures. But that's like the rest of us. So go ahead and try them out. It's a real problem. Vary the lambda values and so forth. So what should you do? Start off with, here are some values. Take 2 mu equals 1, b equals 10. Use at least 16 integration points for precision, because then I can show you the results we've gotten. Okay? So you have to set up the potential matrix, set up the kinetic energy, the Hamiltonian matrix, sum of the two. And what you should observe is that there should be a monotonic relation between the energy as a function of the strength of the potential, lambda. So as you make the strength of the potential greater, or more negative, as the case may be, the bound state gets deeper and deeper. It's not a linear relation. It's a nonlinear relation in the energy, because the energy appears, lambda appears just one place there, but this relation is not linear in any case. And you'll find, especially if you search for the zeros of the determinant, you may find a number of eigenvalues which are not true eigenvalues of the problem, but are sort of numerical eigenvalues only. In other words, as you change the number of grid points, as you make the matrices larger and larger, you increase the precision of the problem. Certain eigenvalues will just change slightly. Others may jump around. So ones that jump around are probably just noise or numerical artifacts. The one that seems to get stabler and stabler changes in the second, maybe the third, fourth decimal place as you get n larger and larger. Those are the good ones. Those are the real eigenvalues. So estimate the precision of your eigenvalue and determine what the best is. So I've given you the hint. The way you estimate the precision is you can see where the energy is fluctuating, which decimal place is fluctuating, and then see that fluctuation gives you some idea of the noise. It may not be true that just increasing n gives you better and better answers. There's round-off error that occurs. There's other numerical errors with the matrices. So you may have to explore this. This is a harder problem than some of the ones we've seen before. And finally, whatever you do, you get answers. You get a psi, you get an energy. Check how the right and the left-hand side of this equation compares. Take the Hamiltonian matrix, you know that, multiply by the wave vector that comes out of the code, and then see if that is, in fact, E times psi. The normalization of the wave vector doesn't matter. You don't have to normalize it. So that's it. Okay, so now let's take a break and look at momentum space wave functions shortly. Okay, so as an optional exercise, you can determine the momentum space wave function. You do not, and I don't particularly want you to have to do this in coordinate space, but I want you to see whether the wave function looks reasonable, get some feel once in your life maybe for what a bound state wave function looks like in momentum space. So, determine psi of k. Go ahead, let's make some plots for what that looks like. For the hydrogen atom, you can look this up in a textbook. The psi of p, the momentum space wave function, varies like 1 over p squared with some constant here. related to the energy. So it should fall off like 1 over p squared in momentum space. That's good. Whatever you get, look at it. Is it reasonable? Is it normalizable? So in particular, if it's not normalizable, it can't be a bound state, because a bound state has to be normalizable both in coordinate space and in momentum space. Then, do it. If you have your momentum space wave function, you think it's reasonable, transform it. Here's the equation using all the normalizations we've used, the definitions. This gives you the momentum space wave function conversion to the coordinate space wave function. We haven't normalized them in any particular way, but that's not an issue. Then look at the drop-off in coordinate space. Is that reasonable? And finally, for the delta shell potential, which is our potential, we know that the wave function in coordinate space has this exponential drop-off, as given here. A drop-off and a growth inside the shell, and there's just a drop-off outside. So is that more or less what you're getting? So if we look at the textbook, you can see some sample wave functions, what they may look like, or from the code. See what you get. So go ahead, enjoy momentum space. We'll be back in a moment to talk about scattering in momentum space, but do the bound states first. Bye-bye.